Okay. So now what's a magnitude comparator? So the screen is visible to you, everyone? Yes or no?
Yes, Professor.
Yes.
Okay. So what we are going to do? So now want to have an n-bit comparator. Since we want to have an m-bit comparator, so what is the size of A? So the size of A is now m bits. The size of B is now m bits. Got it? Okay. Now we are comparing A and B. So now what we are going to do? So now we want to design a magnitude comparator. So now this is our magnitude comparator. So this is a block diagram of a magnitude comparator. We are comparing two quantities, which is actually A is A m minus 1, A m minus 2, and blah 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 until A 0. And then we are comparing it with another number B m minus 1, B m minus 2, and blah 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 until B 0. So what is the size of A? Anyone may help me? The size of A is m bit. And the size of B, what is the size of B? Help me. M bit. So this is actually the block diagram of image. It has three outputs. So the first output we call this as we call it as GT. And what is GT? Greater than. GT stands for greater than, and greater than means A is greater than B. And now we have another output. So basically the other output of this is actually the equal. So I call this as equal, and equal is this if A is equal to B. And then the other output is LT. LT stand for what? Can anyone tell me? Yes, LT.
Less than.
Yes, less than. If A is smaller than B. So these are three outputs. Okay. So now this is an example. So can we see here now what we are going to do? So now we're going to take an example. Okay. So now if you look at here, it's a 4-bit comparator now. In this example, now we have a 4-bit comparator. It is a 4-bit comparator. Now what is a 4-bit comparator? So now M is 4. When M is 4, so now in this example, A is 4 bits. It's the problem. Sometimes this is always a problem with the pen that I'm using. Can you see here now? It is now 4-bit. I don't know why the pen is not working. And now if you see here, okay, now it's working. What is the size of B here? 4-bit. A is also 4-bit and B is also 4-bit. Okay. And then we're comparing A and B. Since we are comparing A and B. Okay. Now can you see here? And this is unsigned number. So what is the value of A here? Can you now tell me what is the value of A here? Can you see here? Anyone may help? If you convert this into binary, help me. So the value of A is 0110. It is actually. Anyone please help me. If you're not interactive, the exam will be difficult.
It's 6.
6.
6. And what is the value of B now? Yes.
10.
10. Okay. So now this is 6 and 10. Okay. Now we have three outputs for this. So can you see here? So now what we are going to do? So this is an example. So the first value of A, if you convert this into binary, it is actually 6. And now the second value is now actually, can you see here? It is actually 10. And now what we are going to do, so now we are comparing, okay, so if we say, oh, there are three outputs, which is actually 6 is smaller than 10. True or false? Help me.
True.
True. If it's true, it means it's a logical one. So 6 is smaller than 10, it's true. So this is actually one. Now using another color, the green color. Okay, now if you see here, so now we have 6 is greater than 10. Yes, true or false?
False.
False. So the second bit A is greater than B will be 0. And now I'm going to have the thing. So this is equal to 10. True or false? It's false. This will be equal to 0. Okay. Assume another scenario. So let's assume we have another scenario. So now if you look at here, so now if you look at this thingy, so this is actually what is this? This number is actually 7, okay, and this number is actually what? 7. So now if you can see here, so let's assume now I'm using the red color. So 7 is smaller than, sorry, 7 is smaller than 7. True or false? False.
False.
So, it means it is 0. So this will be 0. Okay, then again, they're now using the green color. So now you can say, let's assume 7 is greater than 7. True or false?
False.
False. This value will be 0. And now you can see here the other value, which is actually the black color, and 7 is equal to 7. True or false?
True.
True, and it's 1. Any question? And again, we have another scenario. So now we have another scenario. So now let's assume we have another scenario. So in this scenario, what is the value of A and what is the value of B? So B, it is actually 7. The value of A is actually 1011. It is actually 8 plus 4 plus 2 plus 1. 8 plus 2, 10 and 11. So now we are comparing. So this is actually 8 plus 2 plus 1 is actually equal to 11. And we are comparing A with B. A is 11. So now we are comparing this thing. Now I'm using the red color. So you can say 11 is smaller than 7. Okay, this is now true or false?
False.
False. So it means it will give me a 0. And now if you see, now I'm using another green color. So now I can say 11 is greater than 7. Okay, this condition is now true. And this will give me a logical 1. And the third condition, which is the black color. Okay, so 11 is equal to 7. This will give me a false, and it's given a false, it give me a logical 0. Any question? So this the first thing will be actually 0. So 0 it, and the second thing, which is the green color, which is equal to 1, and the black color will now be 0. Any question? Okay, now please look at here. So now, so can you see here, now we go to the next slide. So we assume that we are comparing A and B. Okay, so what about all these events? So let's assume if you are comparing A and B, so all events. So now can you see here, we are comparing A and B. So now we are comparing A and B. So we are comparing A and B. This is comparing A and B. And this will be a m minus 1 until blah 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 until a 0, and then we have b m minus 1 until blah 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 until b 0, and we have three outcomes. So the first outcome is actually the gt. The second outcome is actually the green color, which is actually lt, and the third outcome, which is the blue color, which is actually, let's assume, equal. Okay, there are three outcomes. So this gt is now outcome 1, outcome 1, this is actually outcome 2, and this one is outcome 3. Can anyone tell me all of these outcome? All of these outcome was what? All of these outcome or what? Can anyone tell me or what? Help me. Anyone may help, please. Are they mutually exclusive or mutually non-exclusive?
Exclusive.
Mutually exclusive. All of these outcome, or now can you see here? These are mutually exclusive. And what does mutually exclusive means? So all of these outcome, I mean, this implies that if one outcome happen, other outcome may not happen. So what are the, okay, what is the possible values? So can you tell me what are the possible values of, okay, so what are the possible values of gt and lt and eq? So there are only three possible. Okay, okay, what are the possible values? So now can you see here, there can be eight possible values, but this is actually 0 0 1. This is outcome, was first outcome. 0 1 0 is the second outcome, and 1 0 0 is the third outcome, and other outcomes are not possible. So all the possible, so these are actually the possible outcomes. And if you say, oh, if a is greater than b and a is lt is greater than b, and they are can, so it means that a is greater than b and a is smaller than b. So this cannot happen. This is a valid input or invalid input? Help me. Valid output or invalid output?
Invalid.
These are invalid output, and these are actually valid outputs. Any question? Okay, now what we are going to do? So the best thing is, now we want to do, what we want to do, so now we want to design this thing. So basically now all these outcome are mutually exclusive. And now now okay, now let's assume if we want to have the equality checker. Okay, so what is an equality checker? So this is now the example of an equality checker. So can you see here? So now this is now my inequality checker. This is now we know. Okay, now let's assume if we want to have this n-bit comparator. What is the size of a comparator here in this example? Help me. Can anyone tell me? What is the size of comparator here in this example? Anyone may answer. Yes, why? Do not hear me? Ghala, Hamad, Junaid.
Yes, we hear you, Professor.
Yeah, so why don't you answer? At least speak something. Okay, just tell me. I'm not hearing you. I cannot understand this question. What is the size of comparator in this example? Can anyone help me?
4-bit.
Hmm? In the slide which is shown here, this is now slide is shown. What is the size of
Oh,
comparator here?
n-bit.
It's n-bit. What is shown? The question that I'm asking is anyway. Okay. Now, so can you see here? Now there are three outputs. The first output is actually the output. Then I can say A is equal to B. So this is equal. Okay. Now can you see here? Now, so what will be the C++ code equivalent for this? If since they are all equally exclusive, if A is equal to B, this implies that equal to be what? 1. Okay, and equal is equal to 1, and LT will be what? 0, and GT will be 0, since they are mutually exclusive. So we can also say, okay, now we can say, okay, if equal is equal to 1, this implies that LT is equal to 0 and GT is equal to 0. Okay, can we write something like this? If listen, if we say if GT is equal to 1, what does it implies? Help me. This implies that LT is equal to 0 and EQ is equal to 0. Can we say if, now we can say if LT is equal to 1, less than is equal to 1, what does it imply? Help me. Yes,
GT is
GT and
equal and
EQ equal 0.
GT will be equal to 0 and equal will be equal to 0. Any question? Should we proceed?
Yes.
Okay. Now what we are going to do? So now we want to design. So now can you see here? Now what we want to design? So we want to design an equality checker. And what does an equality checker say? So okay, now we want to design this thing. We want to design anything. So in this particular example, what is n here in this example? Please answer me very quickly, very quickly.
4.
Yes, n is now 4 bits. Since n is equal to 4 bits, and if n is equal to 4 bits, so now if we want to draw the truth table, if we want to, so what we need, so we need one K map with 256 entries. Why? Because you know how many possible combinations are there. There will be 2 to the power 8, which is actually 256 possible combination. Since there will be 256 possible combination, can we solve this problem using K map? Anyone?
No.
No.
No, because this will be very difficult. Okay, so how should we solve this question? How should we solve this question? Can you tell me how can we solve this question? How can we solve this? How can we design a circuit for this problem?
You compare each bit starting from the MSB side.
Yeah, very good. So we compare each other. So now we want to have an equality checker. Okay. So can we see here? We want to have an equality checker. So can you see here what I'm going to do? So what I'm going to do, so I'm going to copy this. So what I'm going to do is I'm taking a screenshot of this. So screenshot of this. Any question? Okay, now I'm going to take a screenshot of this. Okay, and then what I'm going to do, so now can I see here? So we can say, okay, now can we say Now this outer is my eq. Now we want to have an equality checker. So we want to have an equality checker. So we want to have equality checker. Can we say this that eq will be 1 when if, can we say if equal will be 1 if a3 and b3 are equal? Got it or not got it? Or and now we have an and condition now, and a2 and b2 are equal, and a1 and b1 are equal, and a0 and b0 are equal. Any question? Got it or not got it? Okay, now let's assume now what we are going to do. We are comparing bit by bit. We are comparing bit by bit. So can we see here? Can we see here? So let's assume if we want to compare, if we compare, so how can we get this? So can you see here what I'm going to do? So now I'm taking a screenshot of this, and then I'm taking a screenshot of this. So I'm going to take a, how do we know that A3 and B? So okay, now what I'm going to do? Now I'm using the black color. Why I'm using the black color? So because in the black color I'm now comparing A3 and B3. So okay, so now can you see? Now we can say okay, A3. Now we are comparing. So now we are comparing. We are now comparing A3 and B3. So if you are comparing A3 and B3, so we can, so we define some output E3. So E3 will tell me whether E3 will now tell me that whether A3 and B3 are equal. Any question? So now let's assume if we have, so now let's assume if we draw the truth table for this. So we have A3 and then we have B3 and then we have E3. How many possible combinations for A3 and B3 are there? 0, 0, 0, 1, 1, 0, and then 1, 1. Okay, now if you look at here, now you look at the green color. In the green color, are these A3 and B3 are equal or not equal? Help me, please help me, and please be quick. Please be. They are equal. And now for the red color. So now if I go for the red color, are they equal or not equal?
Not equal.
Not equal. So what will be the value of E3 for not equal? Help me.
0.
0.
0 and 0. And what will be the value of E3 for the green thingy?
1.
1.
1. Any question? Okay. Can we say now? Can you see? So E equal will be 1. So now I'm going to say. So now again written. So equal will be 1. Can I write? Equal will be 1 if E3 is 1 and what? Help me. Can anyone tell me? What should I write in the next line?
E0 is 1.
E2 is
E2 is
1.
1
E1 is 1.
and help me. E1 is 1
E1 is 1. And E0.
and E0 is 1. Got it or not got it? Okay. Now, can I write here? Now we can derive the expression for this. So can we write something like this? So it means that eq will be 1 if, so now I want to convert this into a Boolean expression. So eq will be 1 if E3 is 1, E3 dot, then what I can write? Help me. E2 dot,
E2 E dot E1 dot E0.
E1 dot, and then E0 dot. Okay, now in this case, now we define some index. So can you see here? So let's assume, okay, Okay, now in the next slide, I'm going to. So let's assume. So this okay, E3 dot in EQ dot. Okay, now if you want to solve this, okay, now what is EI now? Now I'm writing a very general expression. What is EI now? Can you tell me what is EI now? What is EI? EI is equal to, okay. So EI now is a function of what? Can you tell me? EI is a function of what? I can say EJ now depends on EJ now depends is a function of AJ. Okay. Let's say we want to find this thingy. Then I'm using the purple color. So EJ is now a function of AJ and BJ. Got it or not got it? Okay. Now this is here. What is the value of J here in this example? Help me.
3.
J is equal to 3. And what is now the range of J? Help me.
0 to n minus 1.
Very good. N minus 1. And what is N here? Since N is 4 here, the range of J for this example is 0 is smaller or equal to J is smaller or equal to 3. Any question? Got it or not got it? Okay. Now, if we say, now if we want to have a general n-bit comparator, so n-bit equal comparator, so control C, so now what I'm going to do, so control copy, and then paste option. Okay, now if you look at here, which property, now what I'm going to do, so I'm going to copy this and paste it here. So now I'm going to take, going to take a screenshot of this. So I'm going to take a screenshot of this. Okay, so now this is now A3 and B3. So in general, we have what? AJ, and then what? Help me. BJ, and the output will be what? EJ. So these are four combinations. The first combination is actually, can you see here? So now if I draw it, so now using the black color, so this will be 0, 0, 0, 1, 1, 0, and 1, 1. So the value of this thing, now I'm using the green color. So this will be, these two will be 1 and 1, and these the red color will be actually, can you see here? So this will be 0 and 0. Any question? Okay. So now which gate? So which gate will be used for EJ? So now it means that now EJ is a function of AJ and BJ. Which gate will be used? Can you tell me?
XNOR.
XNOR gate. Yes, this will be XNOR gate. So this will be an XNOR gate. So EJ is now depending on AJ and BJ. Got it or not got it? Okay. Now we did this thing. So now we found the expression for EJ. So now this is for a 4-bit comparator. So now can you see here? This was now the thing for a 4-bit comparator. So what I'm going to do, so control C. And now what I'm going to do, now I'm going to copy one thing here. I'm going to bring one here. Got it or not got it? So now we have a 4-bit comparator. So since we have a 4-bit comparator, so the EQ. So EQ now depends on, so now we want to design a 4-bit comparator. So now I want to draw the complete block diagram of a 4-bit comparator. So we have, please remember, so now we have an input which is actually A3, A2, A1, and A0. And then we have the other input which is actually B3, B2, B1, and B0. And then the output is actually now with the output is equal to, which is the green color. The output is now equal. But now what is equal? Please record. Equal is now depends on what. So now what I'm going to do, so now this is my equal. So now I'm taking a screenshot of this, copy, and then we want to design this thing. Okay. Now, so can you see here what can do? So now, okay. Now what is EJ? Can you tell me EJ? So now can you see here? So now EJ, so EQ is now equal to A3. Okay, so this E3 is now equal to A3 exclusive NOR B3, and then dot. What about E2? Help me. A2 solution or? So this is actually now A3 is solution nor B3 dot, using the green color. This is actually A2 is solution nor B2. Now we have another color. This will be what? A1 is solution nor B1, and then we have the last color. This will be actually A0 nor. Any question? Any question? So now if you look at here, now what will be the output? So the output is now, can you see here? So now the output is now the first, this we have the first solution NOR gate, and then we have the second solution NOR gate, which is actually the green color. Then we have the third solution NOR gate, which is actually the this color. Is it a lecture recorded? Yeah. Okay. Let's record it. Okay. And then we have the fourth solution NOR gate. Okay, what is the first input to the first gate? So it is actually A3 and B3, and the input to the second gate is actually A2 and B2, and the third input is actually A1 and B1, and the fourth input is actually A0 and B0. What does this give me? So this give me E0, this give me E1, this give me E2, this give me E3. But now I'm going to AND all of them. And since we are going to AND all of them, so I'm now using the red color. So basically the AND of all of them, it will give me now the equal. Any question? And can you see here now, this is the block diagram of an equal comparator. So the thing, so this is now the complete block diagram. And it's the same thing as this. Any question? Any question? Should we proceed? Yes. Yes, students. If this is clear or not clear?
Clear, Professor.
Yes, clear.
Yes, Professor.
Very good. So now it's now clear. So now can you see here? So this is now we can now use the thing. Okay, now what I'm going to do now? So I'm now going to do the same thing. Okay, so to implement, so now can we generally say, so to implement a 4-bit equal operation, we need how many solution OR gates? Help me. 4-bit NOR gates. Okay, sorry, 4. Sorry, Control Z.
For 2-bit.
No. 4 2 input exclusive NOR gates, not exclusive NOR gates, and 1 4 input what?
And gate.
AND gate. Okay, now please remember to implement a 4-bit equal operation. So in general, can we say in general? So what I'm going to do is now in general. So Control X, and then I'm pasting it here as an image so that you know. So in general, can we say, so if you want to implement an n-bit equal operation, what do we need? Help me.
And two input exclusive NOR gate.
N to input XNOR gates. Okay, and 1 how many?
One
N
N input. One.
Got it or got it? Any question? Got it or not got it?
Yes.
Okay, now at this point of time, what we did, so now we have implemented an in equal operation. Okay, so now basically, can you see here now? These are my working from my last lecture. So from other, so I will share both of them with you. Okay, so now can you see these are different explanation. These are different explanations. So can you see here? So you can go through all these explanation there. Okay, any question? And this is also, can you see here now, is look at the slide, this is the same thing. So it means that a3 is equal to b3, this is actually e3, this a2 is equal to b2, this is e2, this a1 is equal to b1, this is e1, and this is all how it works. Okay, and then this is e3, 2, and e1, this is already done. Now what we are going to do, so now we can see we already did this, here this thing. Okay, now what we are going to do, design, anyone may help. Now we want to design a greater operation. How can we design a greater operation? Can you tell me? So let's assume if we want to design, so let's assume we have this thingy. So we have a3, a2, a1, and a0, and then we have b3, b2, b1, and b0, and then we want to design gt. How can we design the gate level implementation of this implement? Can you tell me how can we do that? Can you tell me? Anyone may help. If anyone will answer me the correct question, we'll get one bonus mark.
Compare each bit starting from MSB side. You compare each bit starting from the MSB side. So you check if A3 is greater than B3. If it is not, if it's equal, then you go to the next one. You go A2 is greater than
Very
B2.
good, very good. What's your good name?
Ruben.
Ruben, you will get a one bonus mark. Okay, so please tell me. Okay, good. So, so now what we are going to do? So we start with the MSB. So now we want to design a greater operation. So we want to design a greater operation. So we start with the MSB side. I'll explain this one in an example. I will explain this one in an example. Okay. So now, and why examples are always good. So let's assume we have this A insert. Okay. So now we have an A. Let's assume we have an A3, B3, sorry, A3, A2, A1, and A0. Okay? Okay. Let's assume we have a value of A3 is 1. And then we ignore A2, A1, A0. Got it? And now let's assume we have B, which is actually B3, B2, B1, and B0. And then B3, B0 is equal to 0. And let's assume this is 1, 1, 0. Okay. Now, what is the value of B here? Can you tell me what is the value of B here? Can you tell me? What is this value? Help me.
6.
6. The value of B 6. And what is the value of A? Can you tell me in the value of A? Anyone tell me what is the value of A? Okay, I'm now A2 is don't care. Okay, and A1 is don't care, and A2. So can you see what is this weight? This weight is actually 1, this weight is actually 2, this weight is actually 4, and this weight is actually 8. So what is the minimum value of A? Can you tell me what is the minimum value of A? Help me.
8.
8. Okay, the minimum value of A is there when N2. So basically, when it's the minimum value, so if it is 0, 0, 0, this is the minimum value of A. And what will be the maximum value of A?
15.
And it will be actually what? 15, which is actually 1, 1, 1, 1. All of these things. Okay, now let's assume we have a B. Let's assume we have a B, and let's assume this B value is actually 0, x, x, x. Okay, now for B, what I'm going to do? What is now the minimum value of B? Anyone help me?
0. 0.
Yes, it is 0. And now what is the maximum value of B? Help me.
7.
7. Okay, so now the possible value of A is from 8 to 15, and the possible value of B is. So can we say in this scenario, if A3 is 1, so can we see now what I'm going to do? So I'm making a logical argument now. So now this is my logical argument now. So what I'm going to do, so I'm going to take a screenshot of this. And I'm going to have the next slide. So I'm making now a logical argument. And what is that logical argument? I'm saying the logical argument. So my logical argument is this: if so, my logical argument is this: if A3 is 1 and B3 is 0. If A3 is 1 and B3 is 0, GT will be 1 independent of the values of what? Help me please formulate. Independent of the values of what? Can you formulate? I'm not getting your answer. If you do not understand the question, so independent of values of what? So if A3 is 1 and B3 is 0, so actually it will be GT will be 1, the greater will be 1. So it means that A is greater than B independent of the value of A2, A1, A0 and then B3, B2, B1 and B0. It doesn't matter, they don't care. Any question? Because the minimum value of A, so why I'm going to I am giving this argument. So this I'm giving this argument for the reason that the minimum value of A. So now why I'm going to this? So the minimum value of, okay, so in here why I'm doing this argument. So this is why, because the minimum value of A is greater than what? The maximum value of B. Any question? Any question? Got it or not got it? This clear or not clear? I'm not hearing. If I'm not hearing, exam will be difficult.
No, it's clear, Professor.
It's clear? Okay, now I'm making another argument. I'm making another argument. Okay, so now making another argument, because you know all these things will be about like the arguments. So what will be the argument? So now I will making another argument. So this my second argument is that my second argument. Now I'm giving another argument. What if A3 and B3 are equal? So now we have now another situation. Now we have another situation. So let's say we have A3 and A2, A1 and A0. So what if they are equal? So let's assume this value is 0, 1, XX. Got it or not got it? Or, and then the value of B3 is now 0, 0, XX. Okay, so what is this? What A3 and B3 are equal? So in this case, please remember, now A3 and B3, both of them are what? If they are equal, we look into the next bit. So now can you see here? So now if you look at the next bit, so if they are equal, then we compare what? We compare A2 and B2. And if A2 is 1 and B2 is 0, A2 is 1 and B2 is 0, then GT will be 1. Got it or not got it? So we compare A2 and B2. Again, now assume another scenario. So we have another scenario. Let's assume we have A3 and then A2, A1 and A0 and then B3, B2, B1 and B0, and this value is actually 1, 1, XX, and then it is actually 1, 0, XX. So can you see, even in this scenario, A3 and B3 are equal. Yes, A3 and B3 are equal. Yes, they are equal. If they are equal, we need to compare A2 and B2. So if in this scenario, so it means, see, in this scenario they are equal. Yes, then we compare A2 and B2. And if A2 is 1 and B2 is 0, then it means that now GT will be 1. Got it or not got it? Okay, now what I'm going to do, so now we are making now a logical argument. Now we are making a logical argument, and this logical argument is mine in next slide. And please remember please be attentive, because in the exam will be very tricky question. So please and I will ask a lot of tricky question in the exam. Okay. Now, so in general, so let's assume I define a signal gi. Gi says, sir. So gi says, in gi I am comparing two bits. In gi, so in gi we are comparing two bits, which is actually ai and bi. So now this is the block diagram of a gi, and this is actually ai, and then it is actually bi. Okay, what will be the truth table of this thing? So we have ai and bi. We have four possible combinations: 0, 0, 0, 1, 1, 0, and 1, 1. What will be gi? Gi will be what? Help me. So okay, gi will be 1 if a is 1 and b is 0. So gi will be 1 if a is 1 and b is 0. This will be 1. And gi will be what? So in all of these cases, so now in all of the other combinations, so in this combination, can you see here in this combination, gi will be 0. Okay, so this will be 0, 0, and 0. Okay, what is the expression for gi? So the expression for gi, so gi will be 1 if ai is 1 and bi is 0. So what will be this? So it is actually gi is equal to what? Can you tell me? It is actually gi will be equal to gi will be equal to, this will be equal to ai bi bar. Any question? So gi will be 1. Okay, we are comparing bit by bit. If ai is 1 and bi is 1, and what is the range of I? Can you tell me the range of I? What will be the range of I in this example? Anyone may answer for an n-bit comparator. No one is answering.
0 to n minus 1.
Yes, very good. So this will be the range of gi. Okay, now I'm now making another argument. So I'm now making another argument, and I'm going to do so. So that's what I'm going to do. So now we are going back to the another thing, the truth table. So can you see here? Now I'm copying it, and I'm pasting it here. We want to find an expression for gt. We want to find an expression for gt. So gt. So can I say gt will be 1? So gt will be 1 if a3 is 1 and b3 is 0. So admin. So we can say gt will be 1 if g3 is 1. Can I cite? So g3 is 1. So gt will be 1 if g3 is 1. And what is g3? So this is actually if g3 is 1. Any question? Okay. Now we have an or condition. So we have an or condition. So we have or. Okay. What if a3 and b3 are equal? What if? So now this is other condition. Okay. If they are equal, what if a3 and b3 are equal? How do we know that they are equal? So it means that if e3 is 1, so they will be 1 if e3 is 1. So it means that if e3 is 1, so now I'm using another color. So now this is the another color. So if e3 is 1, then what should I need to look into the another bits. What is that bit? Help me. G2. Then we are comparing A2 and B2, or now the other condition is this. What if this is now another condition? What if E3 and what if A3 and B3 are equal and A2 and B2 are equal? So we need to compare A1 and B1. So let's assume I will say, okay, this is A3, A2, A1, and A0, and this is B3, B2, B1, and B0. Let's assume this value is 0, 0, and 0, 0. This will be 1 and 0, and this is actually 0 and 1. 0 and 1. So can you see here? A3 and B3, they are equal? Yes, they are equal. So we cannot say whether A is greater than B. So when we look into the A1, so when we look into the A1, so it means, oh yeah, A1, so it means that A1 is greater than B, so it means G1 is 1. Any question? Any question? Should we proceed? Okay, so now what we are going to do, so in the next thing, so now we are comparing A3. Okay, what should be the next expression? Can you tell me? So now if A3 and B3 are equal, so you see E3, and if A2 and B2 are equal, so E2, what we should go for? So we need to look into the another bit. Then we say G1 or what will be the last expression? Can you tell me? Help me. Help me.
E3, E2, E1, G0.
E3, E1, and G. So this is the final expression for GT. So now what I'm going to do? So now this is my final expression for GT. So now this is the final expression for GT. Control C, and then I'm going to do control the final expression GT. And please remember what I'm going to do now. Now while finding the whole expression, we want to find the whole expression. So we want to find the whole expression. Okay. Now, since now we are using GT. So what is now GT? So GT is now G3. So now we will have. Please remember now we want to draw it, and I'm using the green color for this. So now we have G3. So G3 is equal to G3 or okay, this is another thing. So now I'm using the black color for this. What is this thingy? So this black color is actually, let's assume this black color is this is black color. So now we have another OR gate. This is my OR gate. So we have four input OR gate. The output will be GT. So this is actually T1. So this is actually T1. And then we have the other color. What is this thingy? Let's assume this, if we compute this, let's assume this is T2. This is my T2, and we have an OR gate. And the last thing is, let's assume we have this. This is, let's assume T3. Now we have T1. What is T1? So if you look at T1, it is actually E3 G2. So T1 is actually what? E3, and then what? G2. Okay, what is now E3? Please remember now, what is E3? Because it is equal comparator. So we will use an exclusive NOR gate. And E3 is actually A3 and B3. And what is G2? G2 is actually nothing but, so G2 is actually what? A2, B2 bar. Okay, what is now G3? G3. So G3 is now A3 and B3 bar. So now this is actually, can you see here? So this is an AND gate. So this is actually A3 and then what? B3 bar. Any question? And now we have G2. So for this G2 is actually now an AND gate. And this is actually A2 and then what? B2 bar. Now what is T2 now? Can you see? Now if you look at T2, now if you T2, so T2 is E3, E2. Okay, so this is E3, E2. So now we can say, so this is actually now, can you see here? We have E3 and E3 we can go it from here. Then we have E2 and then VG1. What is E2? So if we go for E2, this will be an exclusive NOR gate. This is actually A2 and B2, and then we can find this. This is actually E2, and then we have G1 here now, and then we can complete the whole circuit. Any question? Any question? Got it or not got it? This is clear or not clear? I'm not hearing. If I'm not hearing, the exam will be difficult.
It's clear, Professor.
Fine. That's clear. Okay. Now, $1 million question now. $1 million question now for all of you. What circuit do we need to design for, like, if what so can you see here, control X? Okay, so we did this thingy. Okay, $1 million. Now we want to design for LT. Since we want to design for LT, we have A3, A2, A1 and A0, and then we have B3, B2, B1, and B0. We want to design for LT. What should we do for LT? Can you tell me what should we do for LT? Can anyone explain? So did we derive the expression for GT? Yes or no? What was the expression for
Yes.
GT? Can you tell me? Please note this was the expression for GT. Help me. Am I right or not? Okay. So what should be the expression for LT? Anyone may answer. What should can anyone tell me what will be the expression for LT?
Should be the same. You should compare MSB. If it's less than, we continue to the next one.
Yeah. So instead of doing this, so if you want to compare it, so we replace G3 with what? L3. So can we write L3 or E3 L2 or E3 E2 L1 or what? Help me. E3 E2 E1 and L0. Okay, please remember. Now what is L0? Okay, now what is Li? Now we want to find Li. So what is the range for Lj? Let's do what will be the range for Lj? We want to compare L. So what will be the range of Lj? So 0 is more or equal to j is more or equal to n minus 1. And now Lj. Lj now depends on Lj. Lj now depends on what? Help me. Aj and Bj. Okay, so what is Lj? So Lj, now what we are going to do? So now what are going to do? So this is I'm going to do this thing. So now, so what will be the expression for Lj? So it means can you say now? Please have the same logical argument. So now we have the same argument. Lj will be 1 if what? If A3 is what? And B3 is what? Help me. Not so AJ is what and BJ is what? Yes. LJ will be 1 if AJ is what? Help me.
AJ is 0 and BJ is 1.
Very good. It's 1. So it means that LJ will be now equal to AJ bar BJ. So now if you go for this expression, so this will be an inverter for A, and then we have an AND gate, and this will give me and this B. Any question? Got it or not got it? And then similarly, you found an expression for, can you see here? You found an expression for GT here. Okay, now when we found an expression for GT, so I'm not going to sort. So can you see here? What I'm going to do? So I'm going to make a very good thingy now. Okay. So control C. So this is very simple. This is very simple now. Now this is now an expression for GT. Okay. So now what we do need to do? So now I'm now using another. So now I'm using a very thing. I'm now going to use a more color. So I'm using this color. So what I'm going to do? I'm going to okay. I can replace it. I can replace this again, and then I can replace this. And I can replace this. Okay, so now this I can replace this. Got it or not got it? But now I can also replace a bar on it because you know this is a, now can you see here? And now then we can see here. Now what I can doing to do? So this is actually because this is L3 now. We want to compute L3. Since we want to compute L3, so A3 has to be 0 and B3 has to be 1. Got it or not got it? Then we have E3, then we have E2, and then we have E1. And then what will be the output here? The output here will be LT. Got it or not? So this is LT, this E3, E2, and 1, A1, and blah blah blah. And this is actually if E3, so E3 and E2 are equal, what should be here the next expression? E3 and E2 are equal. What we need to compare? L1. And if we say E3, E2, and E1 in E0 all are equal, so basically E3 and E2, E1. So basically the expression for this will be L0. So now we are comparing L0 will be here. Got it or not got it? So we have replaced all else with what? G. So now L2 will be here. and then L1, and what will be L0? So if you want to compute L0, so L0 will be what? Help me. This will be actually a 0 bar. And any question? And then you can fill the whole diagram. So you can fill the whole thingy. So now this is the final expression. So this is my LT expression. So you see here. If you look at here, this is my final expression. And you can use this expression for this. Anyone? So we have L3, L0. This is L0. L0 is here. Then E3, 2, 81, and then this is the final expression. Any question? And you can complete the whole diagram. So I'm not completing a field, but if we ask the same question in exams, any question? Should we proceed? If it's
Yes,
not clear,
Professor.
the exam will be clear. Okay, please go ahead. Please at least speak, and please be very quick. I want that everyone is now attentive. Okay. Now, again a $1,000,000 question. Again a $1,000,000 question. This is a very $1,000,000 question. One may answer. If anyone may answer with 5 seconds, we'll get one bonus mark. If anyone will answer in 5 seconds, we'll get one bonus mark. I need your attention now. Assume that we are comparing two n-bit numbers. So we are comparing a n minus 1, b n minus 1, and blah 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 until, sorry, a n minus 1 and a 0. And then we are comparing b n minus 1, b n minus 2, and blah 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 until b 0. Let's say we have two outputs. The first output is EQ and the second output is LT. Okay. Now, how can we design a GT here? Can anyone tell me? If anyone will answer me in 5 seconds, we'll get one bonus one. 1,
Put an inverter.
2, 3, 4.
Not EQ, not LT, and
Not EQ, not LT. Very good. Very good. Very good. That's the thing. Very good. So now please look at here. Now, if you look at here, now we have EQ. Now EQ now depends on, EQ is now a function. We have divided expression on GT. Now GT is now a function of, so can you see here? GT is now a function of EQ and LT. How many possible values are there? 0, 0, 0, 1, 1, 0, and 1, 1. And please remember, since 1, 1, since it is mutually exclusive, this is invalid. It cannot happen. It cannot happen. It is invalid. Okay. Now, if equal is equal to 0, it means that A is not equal to A is not equal to B and A is not less than B. It means that GT will be 1 here. And in both cases, because A is less than B, so GT will be 0 here, GT will be 0 here, and let's assume it will also be 0. So what is GT here? Now, in GT is equal to, so GT will be equal to, so GT, if we want to find the expression for GT, so GT will be equal to, what? Help me. GT will be equal to EQ bar LT bar. And if we apply the De Morgan's theorem on it, so this is a negative AND gate, so it will be equal to something like this. In negative AND gate, or if we apply the De Morgan's theorem, so we can also say, okay, so this is actually EQ plus LT whole bar, so it's in or NOR gate. So basically GT, so the circuit for GT is actually is like this. This is equal and LT, and then we have GT, or GT is the same. So both implementation are correct. So this is GT, and then we have EQ and LT. And using the same arguments, so the same argument. So let's assume if we are given, so what will be the, let's assume we can use the same argument, so we can see that EQ will now depends on LT and GT. And if we, and now can you see here, if we say LT is if now a function of, so it depends on EQ and GT. Any question? Using the same arguments. So if GT and LT is given, so we can find EQ using this expression, and if EQ and GT are equal, you can find LT. Any question? Because of the mutual exclusive property. Any question? I'm not hearing. It means the exam will be difficult. Oh man, exam will be difficult. Everyone wants a difficult exam. Clear? I'm not listening.
yes.
Yes. Now the guy who said yes, he wants the exam to be easy. Okay. So I will make a separate exam for you, man. Okay. So what I'm going to do? Clear? Oh, okay. Now I can also make it for you. The
Professor,
same
it's
thing.
very
So this
clear,
is
very
actually
clear.
the less than output. So these are all the expression for LT, and this is, these are all the arguments. So you can say L3 is in, we did the expression for this, and then so I have already explained all of these things. And now we can say here, we should comparator. Okay, now what I'm going to do. Okay, now the things that has been done, now the thing we have explained all of the stuff. So what I'm going to do, so I'm now going to remove the writing pad, and then I'm going to explain more things. Is the screen visible to you now? Maybe it's unvisible. It's visible or
It
unvisible? Can
is
you tell me?
it is visible.
The screen is
It's not
visible?
visible. It's not
It's
It
visible.
not
went
visible because
now.
because when I remove the pad, so then it becomes not visible. There is a problem with this, but I can So I'm going to do share. No, share application screen. Sorry, share. I want to share the entire screen. Now is the screen visible to you now? Yes or no?
No.
No, Professor.
No, it will be visible.
Okay. Yeah,
Visible.
it's
Okay.
visible.
Now can you see here now what you are going to do? So now if you're doing it in visible, okay, this is the all the expression. So can you see here, this is all the expression. Okay, now now what I'm going to do, so what I'm going to do, so we did all this. Oh no, oh no, oh no, 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 no. Okay, 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 okay. So we are comparing to 4-bit number. So we have A is A3, A2, A1, and 0. B is B3, B2, B1, and we have 0. Okay. We found the expression for LT. Remember, we found the expression for LT. Yes or no?
Yes.
Yes or no? Okay. What is this thing? Can you not tell me what is this thing? Help me. What is this thingy? Anyone may answer. Because A3 is 0 and B3 is 1. It is actually what? L3. And what is this thingy? Anyone may help. Anyone may help.
L2.
This is actually L2. And what is this thingy? Anyone may help. What is this thingy?
L1.
L1. Okay, now again, what I'm going to do now, so now let's say I'm now using this color, maybe this black color. What is this thing? Help me.
G2.
Very good, very good. Now your exam will be easy. If you're paying attention, your exam will be easy. What is this thingy? Okay, what we did, we expanded all the expressions. We expanded all the expression for LT. So this is now the expression for LT. This is now the expression for GT, and we already expanded it. And what is EQ? EQ is actually what? EQ is equal to B E3, E2, E1, and E0. Okay, now can you see here how many times E3 has been used? How many times E3 has been used? Can you tell me? E3 has been used here, use it, blah 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 blah.
5 times?
Any question? E3 is now 7 times.
6? Yeah, 7 times. Okay.
No, 7 times. Why? I'll explain it. Okay. Can you see here? Now look at here. And why I'm doing this? So basically, can you see here? Now I'm going to make it E3. So E3 is used here. So E3 is used here. It is used here. E3 is used here. E3 is used here. 4, 5, 6. Any question? Clear or not clear? And please remember why E3 has been used here. So now what I'm going to do, so I'm now making another color. So maybe I will use some very weird color, maybe this yellow color. So E3 is here. Oh, now this is not visible, but I want to have some color which is more visible. Okay, maybe I will use this purple, this color. So E3 is here. E3 is here, 2, 3, 4, 5, 6, and 7. Am I right or not? How many times E1 has been used? How many times E1 has been used?
3 times.
3 times. How many times E2 has been used?
5 times.
5 times. Very good. So can you see we can go for E2. From for E2 we can say, okay, this is 1 E2. Okay, now I don't know why is this thing. So this is 1. Okay, this is 1, this is 2, this is 3, this is 4, this is 5. Got it or not got it? Okay, now we go to the next slide. So yeah, we're going to do this thing, and we okay. Now please remember, what is this E0? We can also use. Please remember, we can also use an exclusive NOR gate, but we didn't use an exclusive NOR gate. This is the implementation of an exclusive NOR gate and AND gate. Why we are using? Because we want to reuse this. We want to reuse this, the output of this NAND gate and the output. And what is this thingy? Can anyone tell me? Anyone may tell me what is this thingy? And any what is this thingy? What is this signal? Can anyone tell me what is this signal? Help me.
A not B B0. A0 not.
Not. So this is it is actually L0. Got it or not got it?
Yeah, got it.
Okay. Now if you look at here, this output. So can you see here now? If you look at this output, this output. What is this thing? Help me. This point. Help me.
G0.
G0. And please remember, we can say if L0 and G0 bar and we uniquely NOR gate, so this E0 now depends on G0 and B0. Any question? Okay. Can you now tell me what is this thingy? What is this thingy? What is this thingy? Help me. What is this point? Help me. L1. And what is this point? Can you tell me? Help me. The green one. This point. G1. Any question? Should we proceed? This is G1. This is actually G1. Any question? Should we proceed?
Yes, Professor.
Okay, now this is the fan out. Can you see here the fan out of E3 is 7 and then the fan out E3? So this is all the things. So the fan out of the NOR gate and blah blah blah. Any question? What is the fan out of E2? E2 is 5. These all the things are there, and this is any question relevant to today's class? So I will save all of the working on island. I will save all of the working on island for today. Please remind me to sort of okay. So please remember these are these are two workings. This is the first working in the previous class for the section 2, and now it's also include the working for your class. So I will put all of the working. So please you need to know. So this is all the working that I did it for both classes. I will upload all of the workings and any question.
Professor, I actually had a question. Are we still going to have 3 midterms and a final? Like,
Why 3 midterms? Why we have 2 midterms?